model it mostly the load, electrolyzer load, and we saw that the load can be modeled from a very simple static model to it can be involve different stages of dynamic electrical equivalent. Also, it can also involve the electrochemical equivalent model. Okay, so whatever we developed the electrochemical model, if you can see the subsystem here, that is connected to a DC-DC converter. So this is the final version we are going to build today, and this converter also, all the switches, if you see, it is given with kind of control switches. So we will have a controller involved for this DC-DC DAB converter. And basically, if you remember the lecture yesterday, we are calling this as a isolated DC-DC converter. If you see, the primary and secondary are isolated through a transformer, and this transformer is not going to be a low frequency transformer, it's a high frequency transformer. So all modeling details from input side to the load side, and then we'll create some simulation scenarios like disturbances and all, how the controller is tracking and the response we are getting, that we are going to see today. So my student will give you a brief of the theory first, control theory. Basically we'll develop one kind of sliding mode control, which I discussed yesterday, which is a nonlinear control. That control will compare with a PI controller, which is a linear control. And we will see for different case studies or scenarios, what is the response difference between the linear and nonlinear controller. Okay. So he will give a brief of the theory. He will not go into depth, but this model we are going to build along with the controller. So if you have modeled your electrolyzer load, so you can open that model. In the same model, you will build this rest of the system. Okay? Any question? Okay, let's start then.
My name is Satish Kumar, and I am a third year BTech student from NIT Hamirpur, and I came here for my summer research internship under Dr. Animesh Kumar Sahu sir. So first of all, thank you so much sir for giving me an opportunity to stand here and to speak about the work I did during this internship. So basically, in today's simulation section, we are going to discuss and design the nonlinear controller to control the output voltage of our DC to DC DAB converter. So the converter we are using here is a dual active bridge converter, and the control technique that we will use is FIT-SMC, which is fast integral terminal sliding mode controller. So first of all, I will let you know what is DAB converter. So as you can see here, this is a voltage source. We'll give our DC supply high voltage 6000 kV to this DAB converter. After that, these are 4 switches which will convert into an AC voltage. So there is a linear transformer block which will step down this voltage. After that, we will again convert this AC voltage to DC voltage that is going to our electrolyzer load. So the basic principle of DAB converter is that this is an isolated DC to DC converter, and here we are giving 2 pulses to these switches so that our output voltage will come as we want. Is it high volume or not? Okay. So basically, why we are designing controller here? What is the need of this controller? Before that, I will explain. This is a pulse that we are giving to these switches. You can see PWM. This is our original pulse that we will give in 2 switches, alternate switches, and this is note of PWM11 that will give in switch 2 and switch 3. So after that, we will give a phase shift and give to secondary side switches. Our phase shift will decide the magnitude of output voltage. So here we can give as we want the value of phi. We can give pi by 6 or any value we can give here. Accordingly, the output voltage will change. So I want to give this value of phi through my controller, so that in case of any fluctuation in input voltage, we get our desired output voltage. Shall we start to design the controller? How we will design our controller, what is the mathematics behind that? So here is a standard equation of sliding surface of FIT SMC. What we do in any SMC controller, first of all we will design a surface on which we want to slide our controller. If our controller will slide on this sliding surface, then we will get our output voltage as we desired. So this is a standard output voltage, standard sliding surface equation for FIT SMC, where EV is the error function, where V0 star is our reference voltage minus V0 is the actual voltage. So what we will do, we'll differentiate rho, which is a sliding surface, with respect to time, so that we can get EV dot here. So in this equation we can say EV dot is equal to V0 star dot minus V0 dot, and this V0 dot we will get from the dynamic equation of DAB converter. So we are getting rho dot derivative of sliding surface with respect to time, and there will be an equation of S dot also, which we call reaching low, because we want our controller to reach that sliding surface and to slide on that surface. So there will be an equation of reaching low. We'll compare both of these equations, and after that we will get our control input.
So in bit not getting any single point, just raise your hand. We'll again explain, okay?
These two equations, we will get our control input, which we want to give in a DAB converter. And so as these are four terms in these equations I written here, U star, where U star is equal to D into 1 minus D. And what is D here? D is our duty ratio for DAB converter, where D is equal to phi by pi, where phi is the phase angle that we want to give from first pulse to the second pulse in the secondary side. Sorry ma'am? Yes ma'am, yes ma'am. The phase angle. Basically we are designing this controller to get the expression for phase delay shift that we are giving to the secondary side of DC to DC converter. So this will be the mathematics of our designation of controller. So we'll design these equations in simulation section. First of all, I will explain you how these equation will be explained. So this is our DC to DC converter. How the controller will look like. This is our sliding surface equation. I will show you how it will be built by you. After that, this is the equation of control input. This one. And finally, we are getting our time delay from the control input. So a very first of all, sir, please share that PDF in the group of I sent you. Yes sir, this one. Line 2 to 22, exactly same as it is written there.
PDF in the WhatsApp group. I can say line 3 to line 13 are the system parameter, and then control parameter for this FIT SMC starts from line 17 to 22. Okay. On this dot, so basically what you can do, whatever the .m file you created yesterday, same .m file you can write down this also. So single .m file, both converter and load parameter, everything will be there. So you have developed the .m for load parameter, the same thing you update this, maybe below or top, wherever. Open your WhatsApp and see.
Input voltage. V0 reference is our reference value of output voltage that we want, N is our turn ratio, P is our output power, L is sum of leakage inductance and the auxiliary inductance referred in primary side. C naught is our output capacitance, R1 is our load resistance, Fs is our switching frequency. Yes, sir.
Kilowatt, and input voltage is 6 kilovolt, and the secondary we are expecting 262 volt. So we kept this parameter looking at because we say hydrogen electrolyzer is a low voltage high current device. So that's why this high voltage step down we require. That's why keeping that in mind we prepare this parameter. So 6 kV step down to 262 volt. So that current in the secondary will be definitely higher, right? Because transformer principle, power in primary secondary are same. Where we are using in the model. Then we will go to control parameter. Okay.
Design. And in .m file you can see that K1, K2 and B inverse, that is written as
IGBT with an anti-parallel diode. Okay. So IGBT slash diode, that switch we are going to use for this DAB converter. And we will use the default value, we are not changing anything in the switch level. Okay.
After that you can search for linear transformer.
Let them build the bridge first.
Okay.
So carefully build the primary bridge. See how it is connected, and you will see there is a primary leakage inductance involved. Okay. So that you can search simply RLC branch. Can you double click RLC? Series RLC. Series RLC branch, then double click that branch. Can you double click and switch to L, and that value, what is you have to define? L, that we defined in the .m file.
You have to click on L, apply.
So better you run your .m file so that it will be recognized here. We are going very slow. Students, getting? Inductor all of you know, right? First year you have covered network theory. Inductor, resistor, capacitor, all you recognize, right? What is the unit for inductor or inductance? What is the unit? Henry, right? So we are using how much inductance value?
165 microhenry.
165 microhenry we are using. Okay. So open a inductor, connect, and first complete the first bridge. And for time being, the gate of each switch you need not to connect. Okay. The gate of each switch you need not to connect. You leave it as it is. Just connect the primary bridge. You can take and copy paste 4 times, but the connection you carefully see. So in this switch, basically if you compare my theory lecture, the diagonal switch, the first switch I call it as switch 1, its diagonal switch I call it as switch 4. Then the other switch I call it as 2, 3. Okay?
2, 3.
So there is no specific name, I am just telling you diagonal 1 and 4, the off diagonal are 2 and 3. Okay?
Like 1, 2, 3.
Back side. Students, secondary side. So this is going to be called, we call it as a full bridge DAB converter. Okay. We have total 8 switches. First leg and second leg. Okay. And there is secondary bridge. The same inductor, you can take a copy, double click it. We selected L, now we can select for C. And you can connect across the output. And what is the variable name for C? C only, right?
C naught.
Can you double click that C? Yeah, it is C naught. What you define in the .m file. Right? Now we have to connect them through a transformer. Okay? So maybe can we double, and we have to go with two winding transformer, okay. We have one primary, one secondary. So internet is not there. You unselect that, okay. Then it will turn into a two winding transformer. No, you first make it okay. Now you open your actual transformer and show the parameter. So who can tell me what is the primary voltage I will put? Students, what is the transformer primary voltage I should put? Wrong. Tell. Which side the primary? 6000, right? I told you primary is 6000, we are stepping down to 262 volt, right? So that's why the primary side is connected to a 6000 or 6 kV. So for that reason we are giving, if you see, winding 1 parameter, we are giving first parameter for winding 1 is the voltage RMS. So there you can define B in, and B in already we defined as 6000 volt or 6 kilovolt, okay. And we are taking it as an ideal transformer, so we are neglecting the winding resistance and leakage inductance, okay. And the, any question? The important thing is the first parameter. What is the power rating? What is the power rating? You defined in your .m file, right? 500 kilowatt, right? So that's why P value, nominal power, we are giving 500 kilowatt. And important thing here, the frequency of this transformer is not 50 hertz. It is not a low frequency transformer. The frequency we are taking at a higher frequency, and that value we are using here 10 kilohertz. Okay, that Fs. That Fs variable we defined in your .m file. So that makes it as a high frequency transformer. Got it? All of you? Okay, so now we come to the secondary winding thing. So which voltage we want at the secondary? Which voltage? Right? 262. So that's why we put 262 here. But it will take automatically, but you define your V0 underscore REF. And that you already defined in your .m file. Getting? Type the right variable so that your .m file will give you the value. Okay?
Now you can click on apply.
And rest of the thing you need not to touch, because we are not, we can do several things, but for time being make it simple, we are considering ideal cases. Okay? But in reality, all this transformer resistance, leakage inductance might affect the performance. Okay? So this is left for you to examine. Okay? So transformer, now I think your model is ready, right? What we will do now, because we have to, now one thing left, please listen here. One thing left here, first you understand, then do, okay? So one thing you have to do, because these switches are there, right? Now we have two ways. Either we, because these are control switch, so we have two ways. Either we control them open loop or we control them closed loop. So what is the difference? Closed loop, basically we consider the feedback control. If you remember my lecture about control, I will take some feedback signal measurement at the output or input. Those I will pass through my controller. Through that control input, I will generate the switches, switching pulses. And then I give to the switch. So that makes a closed loop path, right? Model, controller, again to model. Now instead of that, what we will do, basically at the undergraduate level, every topology we test with first a open loop structure, open loop control, just to see our objectives are met. Okay, so first we will do how to do the pulses or give the pulses using open loop. Open loop means we are not measuring anything, we are self creating the pulses and giving it. Okay, so can you show the open loop first? So whether it is open loop or closed loop, you have to have some kind of pulse generation scheme. Okay, and for DAB yesterday, if you remember, I told mostly three types are considered. One is single phase shift, double phase shift, or triple phase shift. SPS, DPS, or TPS. The most simple one is SPS. So what does that mean? Single phase shift means through the controller, we generate a phase shift between primary and secondary. So through that, and that phase shift we try to vary. And through that phase shift variation, we see the output voltage level changing. Okay, so that is the whole purpose of the controller here. So we will control the output voltage by controlling the phase shift. If some of you remember, yesterday I gave you a power transfer equation for a DAB. If you remember, I gave an expression something into phi into 1 minus phi. So that phi, that is the phase shift which we are going to control. If you can control phi, you can control the power transfer. If you can control phi, you can control the output voltage. Okay? Or sometimes you have dual control. You control the phi, you control both voltage and current. Okay? So depending upon each and every objective, the end goal is to control the phase shift. Through that phase shift, we generate the pulses. Okay? Now what will in open loop? We are directly generating that pulses without touching any voltage current control. Okay? So for that we will take a simple pulse generator, because you know digital control for a switch, it is either high or low, right? And that with a switching frequency. For instance, inverter, if you have done power electronics course, if I consider sinusoidal PWM, you compare a sine signal with a carrier signal. So sine is mostly 50 years or 60 years depending on the country. And then you have a triangular carrier. That carrier is very fast, I mean high frequency carrier. That can be of frequency of 10 kilohertz, 20 kilohertz. Then you compare them through the sinusoidal PWM scheme, and through that comparison, the output becomes up and low, like a pulse generator. Okay? So that you do through SPWM scheme. But at the end, you generate the pulses. The pulse frequency becomes 10 kilohertz, right? Now the same pulse we are generating, but there is a way how you give the pulse. For instance, in this case, if I generate a pulse, the same pulse I will give to my switch 1 and switch 4, because in first time frame I want my switch 1 and switch 4 to be active during the on period. Okay, so if I consider the total cycle as T, my T on, during that time I want my switch 1 and switch 4 to be on. That means you can consider when the switch is on, that switch you replace by a short circuit. I mean for simplicity. That becomes a path for current to flow. So the DC voltage will send a current that will pass through the switch 1, then inductor, then through transformer, then switch 4, then back to the DC. Okay, that is the T on period. That's why I am giving the same high-low signals to the both switches. Okay, can you give that?
You search for pulse generator, double click on that. Now give it time period as TS that you mentioned in .m file, which is equal to 1 by Fs.
Yeah, that TS what I told, if I consider a pulse on and off, total pulse period is TS. Okay, pulse period is TS, which is basically 1 by Fs. Out of that pulse period TS, it will be on for T on and then off for T off. So T on plus T off becomes TS, right? So during that T on out of TS, my switch 1 and switch 4 will be on. Okay.
After that, we are using 50% of duty cycle. It means T on is equal to T off.
Let me explain the duty cycle. Anybody, students know duty cycle, right? So duty cycle means how much percentage time your switches are on over a total time period. That means T on by Ts, correct? So that is what we are doing. So we are telling these two switches 1 and 4 are on for 50% of the time, and rest 50% it is off, 1 and 4. Okay. Now my question to you, rather than what I should give for switch 2 and 3. Shall I give the same pulse? Just raise your hand, I will ask. Now I will connect the same pulse. Can you connect to 1 and 4 only? So is it correct for me the same thing I give to 2 and 3? If no, what is the reason? No, if let's say I don't know anything power electronics, I simply connect the same pulse to 4 switch. Yes. Are you getting? If let's my switch 1 and 2 at a time on, so that becomes a dead short circuit. It will short circuit the source. Correct? Correct? Getting? If my same leg switches are on at the same time, then the short path current will quickly dead short circuit. To avoid that, what we will do, we make sure that switch 2, 3 and switch 1, 4 don't start at same time. So what should I do? That is the philosophy. Now to do that, what I will changes in the simulation?
But if we give delay, then...
Wait. Any guess backside? Delay is one guess. Any guess? Please guess. There is no cost involved in guessing, right? Okay. Anyone from students? You can answer like you don't know power electronics. It's fair. Yeah, tell. If else means what I will do if else. Correct. That if else, I understand. You want to tell me that if my switch 1 and 4 is on, please don't switch on 2 and 3. That's what you want to tell the controller. How I can represent this in this simulation? I am just giving a hint, let's say the students, undergraduate student. I am giving you, I can give you some logic gates. Logic gates you know, right? So which logic gate is appropriate here? Which one? Please tell. No. XOR not. Yes. Yeah, that we selected by duty cycle. So I generated duty cycle of a pulse so that my total TS by 2 times it is on, and another TS by 2 times it is off. But that on signal I want to give couple of switch, and the rest couple of switch I want to give the off stage, so that in the next part those 2 switches will be on. So it's like complementary. So I will simply use a NOT gate. Okay, I will connect and you check I am doing right or wrong. Okay, can you connect? So you can search, you can do by yourself, search for a logic gate and take a NOT gate. Logic working here, right? When my 1 and 3 is on, 2 and 4 is off. Sorry, 1 and 4 is on, 2 and 3 is off. When 2 and 3 is on, 1 and 4 is off. Correct? The same thing will follow for secondary cycle. I want my switch number 5 and switch number 8 to be on at a time, and switch number 6 and switch number 7 to be on at a time. But there is a catch here. I will not give the same pulse, because what we are telling, we are doing phase shift. So my switch number 1 and switch number 5, they will have a phase shift. If I don't have phase shift, to be frank, switch number 1 signal or 1 pulse should go directly to switch number 5. Okay, but I don't want to even on them together. So what I will do, the pulse I am giving to switch number 1, I will give a phase shift, little bit phase shift phi, and that phase shift I will give to switch number 5. Now the sequence of what I maintain for switch on and off in the primary, I maintain for secondary also. After giving this phase shift, whatever will go to switch number 5 will go to switch number 8. And I will use the NOT gate to that and give to 6 and 7. That is the whole story. Okay? There is a phase shift. We will tell you. So can you create a phase shift on that? We will show the pulses. Once we give it, we will plot the pulses, you see which is going where.
So you can double click on pulse generator.
And the switching frequency will same. Only one pulse we are shifting by angle phi and giving to switch 5. So that angle we will give here phase delay. Okay. So if I am taking switch 1 as a reference, I will give a phase delay with respect to switch 1 and give that to switch 5. Getting? So that delay we give here, but that delay has to be in terms of second. Generally when I say phase, it is radian or degree, but we have to convert to second. Okay?
So first of all, let us understand the mathematics. There is a relation between D and phi. Can you write this equation in your notebook? In radian. And you can write also time delay T shift is equal to D into Ts by 2. That is another equation. T shift is equal to D into Ts by 2. Ts is time paid for switching frequency, switching signal. Now you can place value of D in the equation of T shift. Which is pi by 6. So can you put that value in that equation of T shift?
Phase shift we convert to time, because in that pulse we have to give the phase shift in terms of seconds. Okay, that's what he is telling. adjusting its phase shift, and that is the job of the controller instead of pulse width. No, pulse width we are not changing. Phase shift, this is called phase shift. Single phase shift modulation.
T05 is not changed.
Yes, we are not
Only
changing
phi
it.
is changed.
And SPS, but PS is what? I am just giving an example. I initially shift this with a phi 1, let's say, the S1 S4, and S5 S8 I will again shift to phi 2 with respect to phi 1. So my primary is shifted, secondary is shifted to with respect to primary. That is called dual phase shift. Okay, but here we are keeping single phase shift. We are keeping the primary trend of pulses no zero phase shift and shifting the 5 and 8, and we can use NOT gate to here, and that will go to S3 S2, and here you can use NOT gate. NOT gate means it will be inverted, right? It will go to S6 and S5. Sorry, S7. Okay. So that phi we are converting to time. Now, how much phase shift? Okay. So that T shift you can give T D into TS by 2. Okay. That we are going to use in the simulation.
Become TS by 12. We can write it that TS divided by 12. Apply. Okay.
Okay. So now in the pulse width, you take a copy. Only change you do the phase shift thing where we are giving TS by 12. So can you explain?
After putting D is equal to phi by pi, we will get phi into TS by 2 pi. So by using value of phi, you can use pi by 6 or any value you want, considering it 30 degree.
Yes, so we are considering phi 30 degree here, and that will be in radian pi by 6. Okay, but that phi I am not telling universal. That phi has to be decided based on your closed loop control. We are just showing for a particular phase shift how it operates. Some type is discrete, and sample time you can give 1 e power minus 7. I mean, of course you can take several combination, but there is a thumb rule that how much sampling and how much switching, that ratio has to be fixed. So for our switching we took something like 0.1 microsecond. Okay, so that's why sample time place you put 1 e power minus 7, and simulation time you put discrete.
Yes, sir.
8 pulses we are taking 4 distinguished 4 pulses. Okay, we will show S1, S5, S3 and S7. Signal input, give first signal as S1, second signal you give S5, third signal you give S3, fourth signal you give S6. Just put 4 input to the scope, run for 0.01 second. 0.01 second run the simulation. You also run 0.01. Okay.
S1.
Or something is to check which is second one.
This
Is
node
not
of
connected.
that actual.
S1, that goes to S4 as well. Second one is S2, which is the inversion of S1, right? Not gate. That goes to S2 and S3. The S5, the first signal and third signal, see the starting point, there is a phase shift of 30 degree. Correct? And the same signal is inverted for the switch 6 and switch 7. Understood? This is the operating principle of DAB converter controlled through single phase shift modulation scheme. Can you check here? switching operation, right? We'll now this phi, why it is called open loop? Because we gave it purposefully. But that's not how the controller works or the converter in the model works. It has to be model adaptive or something like that. So now we'll do that shift here and there through a closed loop control, where now we are showing you one type of sliding mode control. Yesterday I told you several types of sliding mode control, right? Also today we showed you the theory. And for that we require some feedback signal measurement, okay? So in this case we are trying to control the output voltage, okay? Voltage across the capacitor. That what we are trying to control, okay? Now we'll remove the open loop switch. We'll generate the switch as the controller output. Our SPS scheme will still be there, but only that control input will be generated through controllers. All of our
Request you to write this equation on your notebook. It will be easy for you. Output voltage as backup signal. So you can search on voltage measurement block.
yeah, so yesterday also you use this voltmeter. So connect a voltmeter across the capacitor and tag it as V naught in or output voltage. Voltmeter, then connect across the capacitor, tag it as V naught. This is the parameter which we are going to control using the principle of sliding mode control, okay? Right, I forgot to mention. Output capacitor across when you finish the secondary bridge, and that capacitance value you put C naught, okay? Can you double click and just go to type, you will get, yes. Because we are tagging it and make it global so that in the controller subsystem we are calling it again.
Make it global.
Voltage now, okay? That will take as a feedback to our feedback input to our controller. So now we'll enter to sliding surface equation, which is the heart of a sliding mode control. That sliding mode equation involves the measurement of a voltage error. So how will you measure the error? So measured value, reference value minus measured value, and reference value we want at the output 262, right? So now we will create a error. So that error how we'll do? We'll take a summation. It is my VO reference. This is what I tagging from output, and the subtraction is voltage error. This is already you defined in your .m file. So what you can do, you can take a constant block, just put the same parameter. So it will call it B naught reference. Here basically this value is 262 for time being, okay? And this will come from block, that is V naught. So that EV becomes B naught reference minus B naught, right? Understood? Calculation of voltage error. Now second step, calculation of sliding surface. Check your document in the WhatsApp. What is the expression for sliding surface? This contains a term called voltage error, right? So what we will do with that voltage error? We will take that, then if you double click you will get something called signum function. Check, double click and sign value. So basically if you see, the sliding surface is consist of three terms. One is directly you take the error, then you add with a constant and integration of that error, then some another tuning parameter, absolute value of that error to the lambda, and signum of that error. Understood? So how many terms are there? So one is EB, one is K1, K2, lambda. These three are your control parameter. You will play with this parameter to achieve robust response. Okay? And this basically designed based on whatever I told you, Lyapunov theory. Okay? Lyapunov theory to analyze nonlinear controllers. So basically some parameter will give you faster response with a steady state error. Some will give you slower response but with an accurate response. So your job is to design those parameters to obtain a trade-off between all the objectives. Okay? So we have done some background work and we have selected some parameter. Now you can open the .m file, they can type the values of the controllers. Okay, we are not using alpha 1, alpha 2, right?
We will use them in.
So we will use that while generating the control input. For time being, you type from line 17 to line 22.